We're now going to spend some time developing tools to evaluate expectations, to actually compute some of these integrals. In the next lecture, we'll connect the Lebesgue integral to the good old Riemann integral. But first, before we go down that calculus path, let's talk about calculus in a slightly different way, in terms of one-parameter families of random variables. We will often have occasion to consider random variables indexed by a time parameter, t, in some interval in the real line. It could be a discrete parameter, but we'll focus on the case where it's indexed by a whole interval right now. Now, later on in this course, we'll study stochastic processes of this form with interesting probabilistic connections between the random variable at different times. But for now, let's consider, as a motivating example, a much more pedestrian case. Suppose we start with a fixed random variable x and consider for each t the random variable e to the tx. This is a non-negative measurable function on our probability space. And so we can compute the integral of it in principle. It will have a well-defined value, which could be infinite. That's the integral of e to the tx against the probability measure in question, which, since we're in a probability space, we might write as the expectation of e to the tx. But what can we do to actually compute this thing? Well, let's just note that if there exists some positive epsilon, such that e to the epsilon times the absolute value of x is integrable, so that this integral is finite, then in fact this will be finite for all t in the interval from minus epsilon up to epsilon. That's just because for any such t, the real number tx is less than or equal to the absolute value of tx, which is less than or equal to epsilon in that interval, times the absolute value of x. And since the exponential function is an increasing function, we'll get that the integral of e to the tx dp by the monotonicity property is less than or equal to the integral of e to the epsilon x modulus dp, or if you like, the expected value of e to the epsilon absolute value of x, which we're assuming is finite. So that means that e to the tx will be integrable for all t in the interval from minus epsilon up to epsilon. Okay, so as long as we can find one time where the thing is finite, when you take its absolute value, then it'll be integrable on the whole interval up to that time, and it's negative. But that doesn't really help us to actually compute the thing. Well, to do that, we're going to think of this moment-generating function, mx of t, as the integral of a function of two variables. It's a function of the randomness in the variable x, the omega in the probability space, and the t, which is just a plain old real parameter. The kind of parameter that, as the variable of a function, we can use calculus with. The question is, how does calculus, differentiation, interface with this expectation? And that's the topic of today's lecture, differentiating under the integral sign. And here's the answer. Here is the theorem, the main theorem, which we will use very frequently in calculations throughout this course. Take any measure space and consider a function of two variables, a time variable in some open interval in the real line, and the probability space, taking real values. Here we'll assume that the values are actually real, but since we can modify things on a fixed set of measure 0, it could actually blow up at some small measure 0 collection of points. There's subtleties there we need to worry about that we'll come back to at the end of the lecture, though. Now this function is a random variable in omega and a nice function in t. Those are our assumptions. Under those assumptions, we will be able to differentiate under the integral sign. Let's be precise about what nice function means. First, this better be an actual random variable. For any fixed t, it should be measurable. Otherwise, we can't even define the integral. as a function of omega for fixed t, it should also be L1 so that we can take the integral. It turns out that we only need to verify that at any one fixed time, and it will follow that it's L1 for all other times. And we'll see in the proof that that is a simple consequence of the mean value theorem from calculus. Now, if we're going to differentiate out of the integral, passing the ddt underneath, then the thing we're going to integrate is the derivative, the partial derivative of that function with respect to the time variable. And if we're going to integrate that, it better be integrable. So the next assumption that we need is indeed that the partial derivative of f with respect to t exists almost everywhere for any t. Now let's be very, very careful here. When we say it exists almost everywhere, I put that before I put the quantification with respect to t. What I mean here is there must be a fixed null set E, independent of time, so that this derivative exists on the complement of that null set. That is a stronger statement than just saying for any time there's a null set, and we'll see why that matters later. Finally, that alone is not enough, that the thing is L1, because a derivative is a kind of limit. And if we're going to take a derivative under the integral sign, it means we're interchanging a limit with an integral, and we're going to need one of those limit theorems for integrals. The most powerful one we have is the Dominated Convergence Theorem. So we're going to set this up to work with the Dominated Convergence Theorem. We need to assume that there is some dominating function g, a non-negative integrable function, which dominates the partial derivative at all times. At least it dominates it almost everywhere. And again, that has to be a full measure set that is independent of time. So under those very precise niceness conditions, this time-dependent random variable will in fact be L1 for all time, and its integral with respect to mu in the omega variable is a differentiable function everywhere on the interval, and the derivative of the integral is the integral of the derivative. So for starters, the partial derivative is a limit. It's the limit as h goes to 0 of f of t plus h minus f of t over h. In particular, since we know the limit exists on this full measure set of omegas, we can work with just the right limit and take the limit as h goes to 0 from above. And since the limit exists, it suffices to just work, in our case, with a discrete limit along the sequence 1 over n. So this derivative which exists is indeed equal to this limit, 1 over n times f of t plus 1 over n minus f of t. Now, let's use the mean value theorem. Since that derivative exists, and we're now going to work at any one of these points in that full measure set where the derivative does exist, by the mean value theorem, this difference quotient is equal to the derivative at some point. We'll call it t star, where that point t star is between t and t naught. That doesn't really matter as long as it's in the interval from a up to b where things are defined. And here's the thing, our assumption, number 4, that there's a uniform dominating function, shows that no matter what that mean value point is, this is less than or equal to g in absolute value. Okay, so that means that the value of the function f at t, which we can write as the absolute value of f of t minus f of t naught plus f of t naught, using the triangle inequality for real numbers, is less than or equal to the difference f of t minus f of t naught in absolute value plus f of t naught in absolute value. Now, using the mean value theorem, we just showed that the first term there is less than or equal to t minus t naught times g, and the second term is, as we stated, absolute value of f of t naught at omega. Our assumption was that this was in L1 and this is in L1, and so therefore this is in L1, which shows that assuming only that f is in L1 at time t0, we actually have that f is in L1 at all times. Great. We don't need to assume that outright. We just need to check it at one point. Now, as for the main meat of this theorem, we need to show that we can pass the derivative through the integral. So let's define the thing we want to differentiate as capital G. Capital G of t is the integral of f of t against the measure mu. We want to compute the derivative. We're going to do that from the definition. The derivative is the limit as t goes to t naught of this difference quotient. Now, g of t is the integral, and g of t naught is the integral of f at the different times. And the integral is linear, so we can pull this factor of 1 over t minus t naught outside the integrals and also factor the integral through the difference by its linearity. So putting that together, this will equal the integral of f of t minus f of t naught divided by t minus t naught. Well, the thing on the inside is the difference quotient of f, and its derivative is the limit with respect to t. So if I want to take the limit as t goes to t naught on the outside, that's the limit as t goes to t naught of this integral here. And to conclude the statement of the theorem, what I'd like to want to show that that is equal to the integral of the limit of the inside. The dominated convergence theorem allows us to do just that. We can pass limits through integrals, provided that the integrand, which depends on the limit parameter, is uniformly dominated by some L1 function. And that's exactly what that fourth assumption in the theorem tells us. And so we can conclude this holds true by the dominated convergence theorem. Note, we stated the dominated convergence theorem in terms of limits of sequences, and this is a continuous limit. But remember, the continuous limit just means that if I take any sequence of points tn converging to t naught, then this limit holds. And so if you want to exactly match the statement of the dominated convergence theorem we gave, you just do this for each sequence tn converging to t naught. You pass that limit through, and you use the definition of the continuous limit to conclude the result. Hence, we can differentiate under the integral sign, provided that all of these conditions are met. So let's look back at our example motivating this, the moment-generating function. Here, our function of two variables, f of t and omega, is e to the t x of omega. Now, is this measurable for each t? Yes, because e to the t blah is a Borel measurable function, and it's the composition of that function with the measurable x that we're dealing with here. Now we need to see that there is some time at which this is an L1 function for the conditions of the theorem. Well, our assumption is that e to the epsilon absolute value of x is in L1, and therefore f of t naught omega, which is this, well, the absolute value of this is less than or equal to that, which you can see easily from the power series expansion of the exponential, if you like. And so, by the comparison theorem, this will indeed be L1 for any t naught less than epsilon. So, for example, take t naught equal to epsilon over 2, and condition 2 is satisfied for all time. Now we need to see that the derivative, the partial derivative of f with respect to time, is well defined at least almost everywhere, and indeed we'll see that it's well defined everywhere, because the partial derivative of this function of t is just x e to the tx. So that certainly exists for all time. But for the fourth and most important condition, we need to see that there is a uniform L1 dominating function for that. So let's be a little bit sneaky here in doing that. Notice that we know that this part, e to the tx, is dominated by this, which is L1. But throwing an x in there, we're not exactly dominated by this anymore. The way to accomplish that is to note that, if t is less than epsilon, then this part is dominated by this with a smaller term than epsilon there. And the leftover 1 minus epsilon in the exponent will be enough to bound that part, because exponentials are bigger than polynomials. So to make that precise, let's fix some alpha in the open unit interval, a positive number strictly less than 1. Then we get that the absolute value of x is certainly less than or equal to e to the alpha epsilon absolute value of x for any positive epsilon and alpha. And so therefore we can compute that x times e to the tx is less than or equal to e to the alpha epsilon absolute value of x times absolute value of e to the tx. And so if we choose t to be smaller not just than epsilon, but smaller than 1 minus alpha times epsilon, a little bit smaller, then we'll get that the second term, e to the tx in absolute value, is less than or equal to e to the 1 minus alpha epsilon, absolute value of x. But those combine to give e to the epsilon absolute value of x, which we know is in L1 and is a uniform L1 dominating function. So what we conclude from this is that, therefore, the partial derivative is dominated by this L1 function for all t less than 1 minus alpha times epsilon. That's true for any epsilon less than 1, and therefore, taking alpha up to 1, it's also true for t less than epsilon. And thus, on our desired interval, the interval from minus epsilon up to epsilon, we do have this uniform L1 dominating function, and we have now satisfied all 4 conditions of the differentiation under the integral theorem. And so we can therefore conclude by that theorem that the derivative of the integral, which is what we call the moment generating function, is the integral of the derivative, which is the expected value of x e to the tx. And that holds true for all t in that open interval around 0. Now we can repeat this argument. If I try to do it again, taking another derivative of this function, I'll get that the derivative of the inside is x squared e to the tx, and I can follow exactly the same steps because x squared is also bounded by this, at least up to a constant. And we can continue repeating this process indefinitely. So by doing so, we'll find that the nth derivative of this function of t on that interval from minus epsilon up to epsilon is equal to the expectation of x to the n e to the tx for all t in the interval from minus epsilon up to epsilon. In particular, that will say that the nth derivative of this function at 0, since e to the 0x is equal to 1, is equal to the expected value of x to the n. And these are what we call the moments of x. In general, none of them may be finite, or we might find that the first and second moments are finite and the higher ones are infinite, or the first 76 are finite, but the 77th and higher are infinite. We'll talk about that a little more as we go. What this argument actually shows is that under the strong assumption that we've made that the random variable has this property, it has an exponential moment, then all of these polynomial moments are finite, and they can be calculated as the derivatives of this moment-generating function at 0. Now that does give one avenue for actually calculating this function, mx of t, if we know these moments, because then we could use Taylor's theorem to reassemble the function from its power series and possibly compute it explicitly from there. However, we should be careful because just knowing all the derivatives doesn't mean that the Taylor series converges. We also need to know something about their growth to conclude that. But actually, we don't need to go that route because we can use the dominated convergence theorem directly here to show that this moment-generating function has a convergent Taylor series exactly on this same interval. Here's how. The statement is that if we have this exponential moment condition holding for our random variable, then the moment-generating function is real analytic, which means that it has a convergent Taylor series at all points of this time interval from minus epsilon up to epsilon. And in fact, that convergent power series is given by this. It is the Taylor series whose coefficients are the moments. So let's prove this all in one shot. We do that with the dominated convergence theorem by considering the partial sums. Let f capital N of t and omega equal the sum up to n of that series, t to the n over n factorial, but without the expectation, just the powers of the random variable itself. Okay? That's certainly a measurable map. And we can estimate it. The absolute value of fn of t and omega is then by using the triangle inequality for finite sums, less than or equal to the sum up to n of absolute value of t over n factorial times absolute value of x to the n. Now, t is in the interval from minus epsilon up to epsilon, and so t to the n is less than or equal to epsilon to the n in absolute value. So this is less than or equal to the sum n going from 0 up to capital N of epsilon to the n over n factorial times the absolute value of x of omega to the n. And now we can also go ahead and estimate that further to be less than or equal to the sum up to infinity, because all of those terms are positive. So by throwing in the terms from n on, we can only increase the sum, verifying this inequality. But that is the power series definition of e to the epsilon times the absolute value of x of omega, which by assumption is an L1 function. And so that shows that this sequence of measurable functions are uniformly dominated by this L1 function. And so we can apply the dominated convergence theorem, which tells us that if I know what the pointwise limit of this is, then the integral of that pointwise limit is the limit of the integrals. What's the pointwise limit here? Well, fn of t dot at any omega converges to e to the tx. That's pointwise convergence on the whole sample space. We're just talking about the Taylor series of the exponential map converging. And so we therefore have, combining this and this by the dominated convergence theorem, the integral, the expected value of f capital N of t and omega converges to the expected value of the limit, e to the tx. There's our moment generating function. But on the other hand, fn is just a finite sum. This is the expected value of the sum up to capital N of t to the n over n factorial x to the n. And that, because of the linearity of the expectation, is the sum n going from 0 up to capital N of t to the n over n factorial expected value of x to the n. So what that tells us is that this, which is the Taylor polynomial of degree n for this function, does indeed converge to this function. So the Taylor series does converge. And since the limit is finite, by the statement of the dominated convergence theorem, we have that the moment generating function is equal to the limit of that, which is how we define that power series. And so there we have it. This is a convergent Taylor series. We know that Taylor series, when they converge uniformly on their domain of convergence. And so we actually get, by standard calculus, that on the open interval from minus epsilon up to epsilon, this convergence is uniform. We also know that we can differentiate convergent power series term by term, and so we again get for free from Taylor's theorem that the derivatives of this function, mx of t, yield the moments. But we also see that the power series, putting them together, converges on at least this interval. We're going to circle back to the moment generating function later in this course and subsequent ones. It turns out to be a very powerful, robust tool for identifying distributions of random variables. Before we go on in that direction, let's make a final plea of caution. When we're applying the differentiation under the integral theorem, it's very important to satisfy all of the conditions precisely. In particular, if you only know that conditions 3 and 4 hold almost surely, it's very important that the almost sure set on which they hold is independent of time. And here's an example to show why. Let's take our measure space to be the Lebesgue measure on the Borel sigma field over the unit interval. And consider the function of two variables, indicator of the set where omega is less than or equal to t. In other words, as a random variable, this is the indicator of the interval from 0 up to t. Now, for fixed t, that's certainly measurable, because the interval from 0 up to t is a Borel set. We also have that this is an indicator function, so it's less than or equal to 1. And since the Lebesgue measure of the whole space, the unit interval, is finite, that means that that constant dominating function is L1. And so there is some time, in fact already automatically every time, at which this is L1. Now, for item 3 in the theorem, let's compute the derivative. We want to take the time derivative of this function of time. So it's better to write it like this. This is the indicator that t is greater than or equal to omega. So maybe we should write this as at omega. That's d dt of the function which is 1 if t is greater than or equal to omega, and 0 if t is less than omega, omega being in the unit interval. That is a locally constant function. It's constant on a bunch of intervals. And so this derivative is equal to the derivative of a constant which is 0 if t is not equal to omega. If t equals omega, the derivative doesn't exist. The step function isn't differentiable. But that's okay. There's just one point where the derivative doesn't exist. And we said in the theorem that this will apply as long as the set of points where it doesn't exist has measure 0, right? Great. So finally, for 4, we need to find a uniform dominating function. But notice that the derivative is 0, almost surely. And so therefore, we can take our dominating function to be 0. It only has to hold almost everywhere. And 0 is certainly an L1, and therefore that condition is also met. So we can apply our differentiation under the integral theorem. If I integrate this function, the indicator from 0 up to t, and differentiate it, it'll give me the same value as integrating the derivative. Well, let's do that part first. The derivative we just computed is 0 almost everywhere. A function which is 0 almost everywhere has integral equal to 0. Okay, so that must be the derivative of the integral. But what is this integral? This is the integral of an indicator function, which we know is just another way of writing the measure of that interval. So this is the derivative of the Lebesgue measure of the interval from 0 up to t. But the Lebesgue measure of the interval from 0 up to t is t, and that gives 1. And these are most definitely not equal. So what happened? What happened is we were sloppy. The set of points where items 3 and 4 don't hold, while measure 0 was very much dependent on the time parameter. It was equal to the time parameter. And since there's an uncountable set of time parameters, the union of those as we apply the theorem all together comes up with a set that is not measure 0, and so the theorem doesn't apply. So be careful when you're applying this theorem. If it's going to be applied to a function where the conditions are only met almost everywhere, that almost everywhere set has to be independent of time.